Hello, am I audible? Hello, am I audible? Can you
Yes,
unmute
sir,
me?
yes, sir, you are audible.
And my screen is visible?
Yes, sir, screen is
Okay,
visible.
okay, thank you. So, good evening, everyone. Welcome to this NPTEL live session for the course Introduction to Machine Learning. So, this is my fourth live session. So, my name is Ayan Maiti. I'm a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. So in this live session we will discuss some practice problems on week 4 topics. So week 4 topics were perceptron learning algorithm and support vector machine. So these were the topics that were covered in week 4. So we will discuss some practice problems on these two topics mostly. And also I will try to answer your questions and queries. So if you have any questions and queries, please feel free to ask. So I can start discussing some practice problems now. So the first question is, consider a boolean function in three variables that returns true if two or more variables output two or more variables out of the three are true and false otherwise. Can this function be implemented using perceptron learning algorithm? So there are three input variables in this boolean function, and if two or more variables out of these three are true, then it is true, otherwise false. So that is the output of the boolean variable. At least two variables are true, then the output is true, otherwise it's false. So can this function be implemented using perceptron algorithm? So there are two options only, no and yes. You can write your answers in the chat. I hope the question is understandable. If you have any doubts about this question, you can ask. So I've got one answer in the chat. Sankarlal is saying yes. Okay. Anyone else? Has anyone else computed this? So in this question, if y is the output, which is a function of x1, x2, x3. These are the three variables, three input variables, x1, x2, x3. So the y will be true if at least two of these three variables are true, and false otherwise. If lesser than two variables are true, then y would be false. So we can and all these three input variables, x1, x2, x3, all these variables are boolean variables, so this can take 0 or 1. So basically the separating function or the decision function, we can write it like this: x1 plus x2 plus x3 greater than equals to 2, because if at least two of these three variables are true, then this value would be more than 2, isn't it? So if this condition is satisfied, x1 plus x2 plus x3 is greater than equals to 2, then y would be true, else y is false. So this is basically the condition. X1 plus x2 plus x3 has to be greater than or equal to 2 for y to be true, otherwise it's false. So basically the decision boundary is x1 plus x2 plus x3 equals to 2. So this is the decision boundary. So if it is greater than equals to 2, then true, less than 2, then it's false. So this is the decision boundary, and this can easily be implemented using perceptron learning algorithm. Basically the weights w1, w2, w3, all these weights are set to 1, and the constant term, which is b, is 2. Because in perceptron we write it like this: w1 x1 plus w2 x2, like this, plus b equals to 0, like this we write, or equals to b. So in this case w1 would be 1, w2 would be 1, w3 would also be 1, and b is 2. So this can be implemented using perceptron learning algorithm, because we can find out these weight values w and b corresponding to the decision boundary. So the answer is yes, sir. So is there any questions or doubts regarding this problem? Okay, if there are no doubts, then we can move on to question 2. So this is on support vector machine, SVM. For a support vector machine problem, let xi be the input instance with label yi. If yi into beta 0 plus xi transpose beta greater than equals 1, where beta 0 and beta are the estimated parameters of the model, then there are four options. Xi is not a support vector, xi is a support vector, xi is either an outlier or a support vector, and option D is depending upon other data points, xi may be or may not be a support vector. So which of these four options is correct regarding xi point? So you can write your answers in the chat. So this condition is given for this point xi with output level yi. This condition is given: yi into beta 0 plus xi transpose beta is greater than 1. So if this condition is given, what can we say about this point xi, whether it's a support vector point or not, or it may be a support vector point or not? So what is the status of this point xi? So Mishti Pandey has written A, which is xi is not a support vector. Anyone else? Has anyone else found out the answer? Pratik Tiare has written option B, xi is a support vector. Okay, so I got two different answers in the chat from two different persons. So I got option A and option B as answers in the chat. Pathik is also saying that, or it can be C also. Okay. Mishti Pandya has written it should be option B, so she changed her answer from A to B. Aditya Chauhan has written D, so I got all 4 options in the chat: A, B, C, D. So the correct answer here is option A, that it is not a support vector point. So for support vector points, yi beta 0 plus xi transpose beta 0, this has to be equal to 1. So this condition must be satisfied for support vector points. Only those points that satisfy this criteria are called support vector points, because these points form the parameters beta and also beta 0. So this condition is satisfied only for the support vector points, and it is the condition is given that this yi beta 0 xi transpose beta is greater than 1. So obviously it is not a support vector point. So option A is the only correct answer here. So option B is obviously not, which says xi is support vector, which is not correct. Option C says it is either an outlier or a support vector. It cannot be a support vector, that's why option C is also not correct. And depending upon other data points, xi may or may not be support vector, which is option D. So it doesn't depend on the other data points. For support vector, this quantity has to be equal to 1. So correct answer is option A. Pratik Tiwari says, but why not outlier? But the option C says either an outlier or a support vector. It can never be a support vector. So you can rule out the option C also from here, because for support vector it has to be 1, otherwise it can never be a support vector. So because of this or, it can never be true. Is it okay? So now we can move on to question 3. Suppose we use a linear kernel SVM to build a classifier for a 2-class problem where the training data points are linearly separable. In general, will the classifier trained in this manner be always the same as the classifier trained using perceptron training algorithm on the same data point? So we are using SVM for a 2-class classification problem, and the data points are linearly separable, it is given. And will the classifier trained using SVM and the perceptron training algorithm be same? So this is what you have to answer, yes or no, whether the classifier trained using SVM and the perceptron learning algorithm would be same. So Raghav has written no, Misty Pandey has written no. So both the answers I have received in the chat are saying no. Pratik Tiwari has written yes. Divya has written no. Mahak has written no. So most of the answers in the chat are no. Only one answer is yes in the chat. Anyone else? So the correct answer is no. So the classifier trained using SVM and the classifier trained using perceptron learning algorithm, those two classifiers might not be same, because the objectives in these two classification algorithms are very different. So in case of SVM, the objective is to maximize the margin, so that the linear classifier or the decision boundary is as far as possible from both the classes in the training data set. Whereas in perceptron, the objective is just to classify all the points correctly, not to maximize the margin. So that is the main difference between SVM and perceptron learning algorithm. So the answer is written here. The hyperplane trained by the SVM will have the maximum margin, whereas no such guarantee can be given by hyperplane identified by the perceptron learning algorithm. So because of the differences in the objective, so if the points are like this, these are the positive points, these are the negative points, so the decision boundary learned by the SVM would be like this, exactly at the middle of these two sets of points, so that this margin is maximized. So it should be equally distant from the closest positive point and the closest negative point, so that it maximizes the total margin, maximizes the margin. Whereas in case of perceptron learning algorithm, it might learn this straight line, it might learn this straight line, it might also learn this straight line. So any of these three straight lines can be learned by the perceptron learning algorithm, because all these three straight lines are able to correctly classify both sets of points, because the points are linearly separable. In the question it is given that points are linearly separable, so any of these straight lines can be learned by perceptron. But in case of SVM, it will learn the straight line which maximizes the margin, so that the points, the closest point, positive point, is equally distant to the straight line as the closest negative point, so that the margin is maximized. So because of that, the decision boundary learned by SVM and the perceptron might be different. Question 4. Which of the following is or are true regarding an SVM model? For two-dimensional data points, the separating hyperplane learned by a linear SVM will be a straight line. Option B is, in theory a Gaussian kernel SVM can model any complex separating hyperplane. Option C is, overfitting in an SVM is a function of number of support vectors. So these are the three options. One or more options may be correct in this question. And Pratik Tiwari has written, perceptron only minimize misclassified data points. Yeah, the objective in perceptron is to correctly classify all the points, both positive points and the negative points. It doesn't enforce any condition regarding the margin or how distant the straight line would be from any of the points. So that's why the classifiers will be different. So in for question 4, you can write your answers in the chat. These are the three options. Multiple options may be correct here. Pratik Tiwari says A and C. Okay. So I've got only one answer in the chat, which says A and C. Aditya Chauhan has written A. So the correct answers here A, B and C, all three are correct answers. So the first option says, for two-dimensional data points the separating hyperplane learned by a linear SVM will be a straight line. So for 2D planes, obviously if we use linear SVM, so it would be a straight line. So this is certainly correct. Option A is obviously correct, and option A is correct. And in option B it says, in theory Gaussian kernel SVM can model any complex separating hyperplane, which is also correct. So Gaussian kernel has the ability to model any kind of complex decision boundaries. Theoretically, it might not happen in every case, but theoretically Gaussian kernels can be expressed as an infinite dimensional mapping. So it can model any complex separating hyperplane in theory. This is also correct. Option C says overfitting in an SVM is a function of number of support vector points. So if the number of support vector points is very high, that shows that the decision boundary is trying to fit all the data points which can be noise and outlier. So it is giving importance to even noise and outlier points. That's why it is signifying those points as support vector points. So if we have a very high number of support vectors, it is a sign of overfitting. So overfitting is a function of number of support vectors. So all three options are correct here. Is there any doubt in this question? So now question 5. For a 2-class classification problem, if we use SVM classifier and obtain the following separating hyperplane. So this is the separating hyperplane, and all these circles and rectangles you can see, these are all points. So these are two sets of points it shows, and we have marked 4 instances of the training data. So this 1, 2, 3, 4, these points or instances are marked. Identify the point which will have the highest impact on the shape of the boundary on its removal. So if we remove point 1, how much it would affect the decision boundary. If we remove point 2, how much it would affect the decision boundary. So which of these points would have highest impact on the shape of the boundary if we remove that point. So there are 4 options, 1, 2, 3, 4. So which of these 4 points among 1, 2, 3, 4 will have highest impact on the shape of the decision boundary if we remove that point. Pratik says 1, Sankarlal says A, which is 1, Amrita says 1, Pratik is saying A, Sushanta is saying A. So all the answers in the chat are option A. Satyam is also saying option A. Correct answer is option A. So from this figure we can identify that these are the points which are support vector points. These are very close to the decision boundary. So these points can be guessed as the support vector points. Obviously we cannot say without the exact locations of the points or the coordinates of these points, but we can guess that these points are the support vector points, and the decision boundary, basically the beta and beta naught. So these coefficients or the parameters of this model or of the decision boundary depends on these support vector points only. So if we remove this point 1 from here, so this beta and beta 0 would change, and if this beta and beta 0 changes, then the decision boundary this decision boundary would also change. But if we remove point 2, 3 or 4, these would have no almost negligible effect on the decision boundary, because these points are not support vector points. So beta and beta 0, these coefficients would not change if we remove 2, 3 or 4. But if we remove point 1, then we can see a drastic change in the shape of the decision boundary. So that's why option A is the correct answer. Question 6. State whether true or false. After training an SVM, we can discard all examples which are not support vectors and can still classify new examples. So there are two options, true or false. So it says after training the SVM, if we discard all the examples which are not support vector points, we only keep the support vector points, can we still classify new examples or test examples? Pratik says true, Sankalal is also saying true, Susanto is saying A, which is true. Satyam is saying true, Mahek is saying true. So all 5 answers are true in the chat. So in SVM, the coefficients of the model or the parameters of the model only depends on the support vector point. So beta can be expressed as summation of alpha I, xi, yi, and I belongs to support vector point. So S is the support vector points. So it depends only on the support vector points, because for non-support vector points this alpha I would be 0, and alpha I is non-zero only for support vector points. So it's only support vector points contribute to beta, and non-support vector points cannot contribute to beta, and the beta is beta and beta 0. These are the only two things that we need for constructing the decision boundary and also to classify new examples. So from this expression we can see that we can discard all the other points. We can only keep the support vector points, and we can construct the decision boundary, and we can classify new examples. So option A is correct answer yet, which is true. Question 7. So below are labeled instances of two classes and hand drawn decision boundaries. So for the same data set, we have drawn 3 decision boundaries A, B and C. Which of the following figure demonstrates overfitting of the training data? Sankarlal and Pratik, both of them are saying option C. Mahek is saying option C. Nana is also saying option C. Satyam is saying option A. Durga Prasad, Susanta, Divya are saying option C. So almost all the answers in the chat are option C. So the correct answer here is option C. So overfitting can be defined as in case of overfitting, we try to closely fit the data, or we try to correctly classify even the noise and outlier points. So from this diagram we can see that these points are noise points or outlier points, because these are belonging to this cross class, but these are situated within among the round classes. So that means these points are noise points or outlier points. So this first classifier A is not giving much importance to those noise points. These noise points are misclassified, so it is not giving much importance to those. And in B we can see that two noise points are misclassified, but overall the classification is good. Most of the points are correctly classified. And in option C we can see that all the points are correctly classified, but the decision boundary is very complex, and it tries to correctly classify even the noise points. These points are noise points, and it is giving too much importance to the noise points or the outlier points, so which is not really required. It makes the model much more complex, and it loses its generalizability. So option C is the correct answer here, and option C is in option C the decision boundary is overfitted. So in figure 3, option C, decision boundary is complex and unlikely to generalize the data. So that's why option C is the correct answer. Is noise and outlier points can be called same? Yeah, I mean noise point means which those points and outliers are basically same. I mean outlier means it is not within its own class. It belongs to positive class, but it is situated among the negative points, and noise is also the same. So noise points and outlier points are basically same. Now we can move on to question 8. So this is on SVM again. A hypothetical SVM model has the following values of Lagrangian multipliers and support vectors. So these alpha values are the Lagrangian multipliers, and these are the support vectors, and these are the y or the output levels of those support vector points. So compute the coefficient beta of the linear separator without the intercept term. So you don't have to compute the intercept term, only the coefficient terms beta you have to compute from this table. Alpha support vector points and the y values are given for the support vector points. From this data you can find out you have to find out the coefficient beta, which again would be a vector of the length 3, because the support vector points are of length 3, you can see. So support vector points are length 3, so the beta would also be a vector. So compute this beta and write your answer in the chat. Pratik Tiwari has written not sure but minus half. So beta, the coefficients, beta would be a vector, not a single point. Because you can see these support vector points, this second column, each of these points are vectors, 1 minus 1 1, 0 2 minus 1, and minus 1 0 2. So all these points are vectors of 3 dimensions, of length 3 basically. So beta would also be a vector of length 3, not a scalar like minus half. Pratik says sum of product formula of beta can be applied here. I can't understand what you mean by sum of product formula of beta. I'm not able to understand what formula you're talking about. Shankarlal says 1 1 minus 1. Okay. Anyone else? So this is based on a formula. So if you have gone through the video lectures or the material of this week, then beta can be expressed as a function of this alpha support vector points and the y values for the support vector points. So there is a specific formula for that to easily compute this coefficient vector beta. Has anyone else computed this? Pratik says 1 1 minus 1. Okay, so beta can be expressed as summation of alpha I yi xi, where I belongs to the support vector points. This is the actual formula that you have to use here. The alpha I values are given in the first column. Support vector points, which are these xi, these are given here. So these are the xi points, and these yi values are given in the third column. So these are the support vector points. Xi are the support vector points, ith support vector point. So you have to use this formula. Now if you use this formula, so obviously support vector points are of length 3, vectors of length 3, so that's why beta would also be a sum of 3 vectors in this space. So beta would also be a vector of length 3. So if you compute this, first we would get 1 minus 1 1 plus, for the second we get minus 1 into point half, so minus 1 into half into 0 2 minus 1 plus 1 into minus 1 into minus 1 0 2. So basically you have to compute this. If you compute this, I think this should be the answer, using this 2 minus 2 minus 0.5. So I've got two answers in the chat. Sankarlal and Pratika saying 1 1 minus 1. So did you use this formula, or you used some other formula to get your answers? 1 1 minus 1.
I have used the formula written by beta is summation of alpha I yi xi.
This is the formula, right? Which is I'm showing in this.
I would have made some mistakes in calculation.
Yeah, so I think the answer would be 2 minus 2 minus 0.5, if I have not miscalculated it, but you can recheck it once whether this would be the correct answer. But this is, yeah, this is the formula. So Pratik is also saying the same answer, 1 1 minus 1, but I'm not getting the same answer. Let me check once. So this is what I have. So the first component would be 1 minus half minus half plus 1. And second component would be minus 1 minus 1 0. Third component would be 1 plus, so plus half minus 2. Oh sorry, this one would be 0, so it would be 2 minus 2, and this is minus 0.5. Yeah, so yeah, this is the correct answer, 2 minus 2 minus 0.5. so if you compute it correctly, you would get this answer, 2 minus 2 minus 0.5. so there might be some miscalculations in your calculations.
So please explain once again.
So alpha I yi xi, this is the formula, and sum it over for all the support vector points. So for the first point, alpha 1 is 0, alpha 1 is 1, yi is plus 1. so for the first row I am talking about, alpha 1 is 1, y1 is 1, and
Sir, please move back previous slide.
I mean I don't have much space here, so that's why I am showing.
Okay.
And x1 is 1 minus 1 1. x1 is a vector because it's a point, support vector point. So this is for the first point, alpha 1 y1 x1. Now multiply all three, alpha 1 y1 x1. so what we will get, 1 into 1 into 1 minus 1 1. so these are just scalar multiplications to a vector, so it would remain 1 minus 1 1. Now for the second point, alpha 2 is 0.5 for the second row, 0.5, y2 is minus 1, and x2 is 0 2 minus 1. Now again multiply alpha 2 y2 x2, so alpha 2 y2 x2, and we will get 0.5 into minus 1 into 0 2 minus 1, and again scalar multiplication to this scalar multiplication to this vector. so it would be first component is 0, so first component would be 0, whatever you multiply with it would be 0. For second component would be half minus 1 into 2, so it would be minus half, so minus 1, and third component is 0.5 0.1 and 1, so it would minus 1, so it would be 0.5, it would be 0.5. so similarly you calculate alpha 3 y3 x3. so you have alpha 1 y1 x1, alpha 2 y2 x2, and alpha 3 y3 x3. then just simply add these three, alpha 2 y2 x2 plus alpha 3 y3 x3, and that would give you beta. So this is what you have to do, you have to individually calculate this alpha I yi xi for each of the support vector points, and then sum this up.
Okay, sir, I got it.
Yeah. So now moving on to question 9. Suppose we have 4 training examples in 2 dimensions. The positive examples are x1 equals 0 0, x2 equals 2 2, and the negative examples are x3 equals h1 and x4 is 0 3, where h is between 0 to 3. H is being used as a parameter, so it is an unknown here from 0 to 3. How large can h be so that the training points are still linearly separable? So you have to find out the maximum possible value for h, so that the points, positive examples x1 and x2, these are the positive examples, and the x3 and x4, these are the negative examples, so that these points are still linearly separable. What can be the maximum value of h so that points are still linearly separable? h equals to 0, Pratik says, but h is a continuous variable, so it's not that it can only take 0, 1, 2, 3, 4. It can take any value between 0 to 3. This condition is simply given that h is greater than equals 0 and less than equals 3, and it's a continuous variable, so it can take any fractional value between 0 to 1 or 1 to 2 or 2 to 3. Sankarlal says h equals 3. Srijan says h is less than 1. H less than 1. Okay. 1 is the largest, Srijan is saying. Yeah. Pratik Tiwari says 0 less than equals h less than equals 1. So basically same answer as Srijan, that h is less than 1. So if we simply plot these points, so this is the 0, 0 point. Here we will have this 2, 2 point. These two are positive examples, so I will use a different color for the negative example. x3 is not known exactly because it's h, 1. x4 is known exactly, so which is 0, 3. So let me just increase this. So x4 can be here, which is 0, 3, and x3 we don't know, but as the y coordinate is 1, so it would be somewhere on this line of straight line of y equals 1. This is the straight line y equals 1. It can be anywhere on this straight line because h is not known. So we need these positive examples and negative examples to be linearly separable. So this is the line if we join this x1 and x2 point, 0, 0 and 2, 2, and this is the negative example here. So x3, which is h, 1, has to be anywhere in this region, isn't it? If x3 is somewhere here or here or here, the points are not linearly separable in that case. So x3 cannot be in those places. It has to be to the left of this straight line. To the left of this straight line it has to be. So at max it can be here. At max it can be here. This color is not visible. At max it can be on this straight line exactly, I mean just left to that straight line, and this point is 1, 1, because y is 1 and this straight line is simply x equals y, so x should also be 1. So this point is 1, 1, which is h, 1 in case of x3. So h has to be less than 1. It cannot be less than equals 1. In that case it would be exactly on this x equals to y straight line. So it will in that case it will again be not linearly separable. So h has to be less than 1. So highest value that it can have is 1, largest is 1, but it has to be less than that. So h less than 1. This is the correct answer. Durga Prasad is saying 1. So yeah, 1 is the correct answer. It has to be less than 1, not less than equals to 1. So yeah, Srijan, Pratik and Durga Prasad, all of them have written the correct answer in the chat. So is this solution understandable? my screen visible now? I lost internet connection for a while.
Sir, the point 1 is a positive or negative?
It is negative point, so this x3 here, which is h comma 1.
Sir, am I audible?
Yeah. Okay. H 1 comma 1, which is h comma 1, is this x3 point, which is negative. So that's why we need. Yeah.
Sir, how can we can identify the negative point and positive point?
No, it is already given in the question that positive examples are x1, x2, and negative examples are x3 and x4. And for x3, you have to find out this value of h.
Sir, in this 2D diagram, whatever coordinate you have drawn, that is point 2 lines in x and y coordinate is x coordinate, and 3 lines in y axis, 0 line is y axis, and 1 is the third coordinate. So how we can measure that which one coordinate is positive or negative?
Coordinates, this quadrants don't have to be either positive or negative. Points are positive or negative. These x1 and x2, these 2 points are positive points. x3 and x4, these are the negative points. So now we have to find out what should be the largest value of h, so that the points, positive points and negative points, are linearly separable. So basically you have to find out where can we place x3 so that it is still linearly separable. x3 and x4 are the negative points and they have to be linearly separable to x1 and x2. Quadrants do not have to be labeled as positive, negative. Points are labeled as positive and negative.
Sir, we can draw the linear line between x1 and x2. Apart from x1 and x2, we cannot draw linear line.
We can, but this is the maximum value that h can have. I mean, the h cannot be the x3 point for which we are trying to find out the value of h. x3 cannot be here. If x3 is right to this straight line, joining straight line, if this is the position of x3, then the points are not linearly separable. One negative point is here at 0,3. One negative point is here at x3. So certainly points are not linearly separable. We need the points to be linearly separable. It can be separated like this, where these are the positive points 0, 0, 2, 2 and the other 2 points are negative, but it is not linearly separable. Linearly separable it is possible only if the point x3 is anywhere here to the left of this joining line. In that case it would be linearly separable, and the largest that it can go is this joining straight line.
Okay, sir, I got it.
So that's why h has to be less than 1. So that is the correct answer. Now question 10. So this is the last question of the session. A kernel function k x comma z, so x and z, these are the two vectors or points given. Measure the similarity between the two instances x1 and x and z in a transformed space. For a feature transformation x to phi x, the kernel function is k x comma z phi x into phi z. Consider the two-dimensional input vectors x1, x equals x1 and x2. So for this kernel function k x comma z equals 1 plus x dot z. So this is a dot function or product basically for the same that is product dot product for the vectors x and z. What is the corresponding feature transform phi x? So for this kernel, this is the kernel function given. So what can be the feature transformation from x to phi x? So 4 options are given for phi x. First option is phi x equals x1 comma x2. Second option is phi x is 1 comma x1 comma x2, and third is phi x equals x1 square x2 square, and fourth option is phi x is 1 x1 square x2 square. So for this kernel kx comma z, this is the kernel function. What is the transformation from x to phi x? So this question might be a little difficult. So kernel of x and z, so this is given that it is x dot z, and x is a two-dimensional vector. This is also given here. X is a two-dimensional vector, x1 comma x2. So similarly z is also two-dimensional, z1 comma z2. So if we expand this x dot z, so this is a dot product, so it will be 1 plus x1 z1 plus x2 z2. So this is the expression if we expand the kernel. So we can represent this as a dot product of two vectors, 1 x1 comma x1 comma x2 dot 1 comma z1 comma z2. So it will be z x2. So dot product of this vector and this vector. So basically this is the transformation. Kx comma z is phi x into phi z. So we can write this whole expression as phi of x into phi of z, where this phi of x is 1 comma x1 comma x2 and phi of z is 1 comma z1 comma z2. So this is the phi transformation on x and z. So basically we represent this kernel kx comma z as a vector product of two vectors, dot product of two vectors. These are the two vectors, and these vectors represent the transformation map or the phi x for the vector x. So the correct answer would be option B, 1 comma x1 comma x2. So option B is the correct answer here. So these were the questions that I wanted to discuss on this live session. So now if you have any questions or doubts regarding any of the problems that we discussed today, you can ask me now.
Sir, could you explain about SVM kernel?
SVM kernel, so it would take too much time, and also the video is already there in this week's as the week 4 topic, SVM kernel, so you can study from there. So in the main idea in SVM kernel is that we want to map the instances like x or x1 or x2 or x3 different points to a higher dimensional higher dimension, so that it can use non-linear separability also. So if we use just x as x, so it would be linearly separable only. But if we transform it to x to quadratic form, like 1 comma x1 square comma x1 x2 square, or even the Gaussian kernel, where it is basically e to the power x square it, so in that case it becomes infinite dimensions. So basic objective in kernel is to map it to higher dimensions, so that even if the points are not linearly separable, we can find out a complex hyperplane to separate the two sets of points. So you can check out the video again. If you find it difficult, you can check videos in YouTube of other ML courses. The SVM kernel is a standard topic that is always taught in SVM, so you can check out in YouTube also.
Okay.
Sir, one small doubt.
Yes.
If I use a higher dimensional kernel, then
Yes.
the margin will increase.
Higher dimensional kernel, the margin, I mean, if the points,
Instead of x squared, if I use x cube,
yes,
then what will happen to that margin?
no, the margin is always scaled down to 1, isn't it? We scale the coefficients beta and beta 0 such a way that margin is kept to 1. So we don't have to worry about margin if in case of kernel transformations. So kernel transformation is done if the points are not linearly separable. So if we use just the linear version of these points, the points are not linearly separable. So we transform the points to higher dimensions like x square, x cube, or even exponential or Gaussian kernel. In that case, the points might become linearly separable. So that's why we don't have to worry about whether the margin increases or decreases. If in that higher dimension, the points are linearly separable, the objective of SVM would be to maximize that margin only. So we don't have to worry about whether margin would increase in case of higher dimension or not.
Okay.
So if there are any other, is there any other questions or doubts? So if there are no questions or doubts, then we can end this meeting here. Thank you everyone for joining. We will again have a live session next week for week 5.
Thank you.
Thank you.